Okay, so we've already established in our prior work that electrons want to be isoelectric, right? So if you remember from lecture a couple weeks ago, iso means the same, and electric refers to electronic structure. So in other words, everybody wants to be the same electronic configuration as the noble gases. That's stable. In most cases, that means that we need to form an octet, 8 electrons, because that's what the noble gases have. So for example, with helium. No, let's go to neon, right? So neon has the core of helium, and then you go 2s2, 2p6. So we can see neon has a noble gas core of helium, and then you add on those 8 valence electrons. These 8 valence electrons are what make noble gases so stable. So everybody wants to be like that. And so if you can get 8 valence electrons in every atom in a compound, that will be a happy compound. So let's think about sodium just as an example. Sodium is in group 1, so it has 1 valence electron, which we are going to show as a single dot. Each valence electron is a dot. These are called Lewis dot structures, so dot means electron. And we know that chlorine likes to react with sodium. Chlorine is in group 17, so it's going to have 7 valence electrons. When we fill these in, it's a handy thing to do to fill them in one at a time on each side. So we'll do 1 dot on top, this side, the bottom, this side, and then we'll keep going around. This is kind of like the Aufbau diagrams, except we're not looking at orbitals at this point. We're looking at physical space. So we can have 2 electrons pair up, one going up, one going down, on each side. So this is our 7 valence electrons that chlorine naturally starts with. When it reacts, the sodium is just going to give up this electron to the chlorine. And so in the end, what we end up with is sodium missing 1 electron, so it's going to have a positive charge, because you can think about it has 11 protons and 11 electrons here, including the core. And if you take away 1 electron, you're going to have 11 protons and 10 electrons. So your charge is always equal to the number of protons minus the number of electrons. So that's where we get the positive from. In other words, we have 1 extra proton compared to the number of electrons in that ion. That's because it gave it away. All right? And so then chlorine is going to end up with 8 valence electrons, right? And so to show the charge on chlorine, because we have all these dots, I like to draw brackets here and then put the minus outside of the brackets. So if we think about this, about the electron configuration instead of just total proton and electron count, this can give us some insight into, how this works. So there's the configuration of sodium. And chlorine is going to be kind of similar, except, oh, not 6. Oh my gosh. Oh, hold on. It's in group 17, so it only has 5p electrons. Oh, but hold on, that was correct. I need to be in the right period first. Okay. So 2p6, 3s2. Here's where my 5 go, 3p5. So this will be 2, 6, 8. Yep, okay, good. So this is our starting configurations for both chlorine and sodium. Now, we remember from our work with electron configuration, you're going to lose the highest electron in your list. So in this case for sodium, that's the 3s1. So this becomes 1s2, 2s2, 2p6. That is isoelectric with a noble gas, with neon. Oh, it was right there. Look at that. So that's the same electronic configuration as neon. So we could have also just written the core like that, and that is equally accurate. That means that this ion is stable. On this end of things, we add the electron to the lowest energy that's available. So that's going to be the end of our list. We're going to go 3p6. That makes this isoelectric with argon. So both of these become stable by creating an octet on the chlorine, and hidden inside of the core electrons we also have an octet in the form of being isoelectric with neon, 2s2, 2p6. There's your octet. We don't draw the core electrons in Lewis dot structures, but we do need to understand that when a metal has an isoelectric configuration as an ion, that's stable. That's what our picture is showing here. So this is how an ionic bond gets drawn. And we can do the same thing for a more complicated molecule, right? So we have magnesium, which is in group 2. So 2 valence electrons for magnesium. Chlorine is going to look the same. But I have 2 of those. And the reason for that is that one of them is going to get given away here to make an octet for chlorine. But then magnesium still is not isoelectric with a noble gas. So we're going to have to find another chlorine. And so when we were balancing compounds by changing the subscripts, the reason you have to have 2 chlorine is because you have a +2. That's because it has to give up 2 electrons. And each chlorine can only take 1 of them. All right, so in the end, our final configuration is going to be magnesium having given up 2 electrons. And we're going to have 2 chlorine atoms that each absorbed 1 electron. So it's going to look like this. That's how you draw a Lewis dot structure of an ionic compound. Okay, they are separate little pieces. Now, if we want to draw more complicated structures, mainly covalent bonds because they're interesting, we're going to use these kind of steps. The first thing to do is count the number of valence electrons in your molecule. And then you're going to just kind of try to fit them in so everybody gets 8. Each atom gets 8. Sometimes we're going to share electrons to achieve that, right? That's what a covalent bond does. There's only a few exceptions to the octet rule. Some things don't need 8, and we're going to kind of explore those as we go along. The main one in the beginning is hydrogen. Hydrogen can only have 2 valence electrons assigned to it. It just does not have enough protons to support 8. So just 2. And then so mathematically, and by the way, there's a lot of approaches to Lewis dot structures. If you don't like this one, I have about 5 other worksheets I can give to you that have different methods. This is a mathematical way of solving the problem, but if you like trial and error, I can give you that. If you like drawing, I can give you that process. So come see me in office hours if this one doesn't work for you. There's a lot of options. Anyway, so once we know the total number of electrons and we have figured out how many we need for everybody to have what they need, hydrogen being 2, helium being 2, everything else is 8, we're going to subtract the value from number 2 minus the value from number 1, and this will tell us how many electrons we have to have in bonds. Then we're going to divide that by 2 to figure out how many total bonds there are. So a bond is defined as 2 electrons. And so we divide by 2 to figure out how many bonds to fit into our structure. And so generally we have a few rules in step 5. These are important to reference as you're beginning this process. Carbon always bonds 4 times. That's a hard and fast rule for our class. The rest of them can be different, but carbon is always 4. If you make a structure that has any other number of bonds, then do it over. And then we can figure out how many extra electrons, we call them lone pairs, by taking the number of bonding from the original number we had. And that's whatever is left there, you're going to fill in to satisfy octets. So for water, as an example, we get 1 electron per hydrogen because it's in group 1. Oops. I was doing the math in my head, obviously. So we're going to go 1 plus 1 for each hydrogen. And then oxygen is in group 16 which means it has 6 valence. So if you want to connect this to our our electron configurations, hydrogen's got 1s1, and oxygen is 1s2, 2s2, 2p4. So only the valence electrons count, which is everything after the noble gas core. So here we'll have 6 electrons. So you can either use the periodic table to help you count it, where the main group elements are just, like we said before, 1, 2, 3, 4, 5, 6, 7, 8, like that. So 16, group 16 has 6. Or you can write out the configuration with the noble gas shorthand, and everything after that is your valence. That can get tricky when we're looking at the transition metals, but for now this would be a good place to start. So I have 8 total electrons. If everybody has everything they want, the oxygen would have 8, and the hydrogens would each have 2. So that's how many everything would want to be happy, and so we're going to say that's 12 electrons. So our next step is to subtract those. So we're going to have 4 electrons that are in bonds. To figure out how many bonds that is, divide by 2, we'll get 2 bonds. Well, the next thing to know is when you do Lewis dot structures, the first atom is the central atom, unless it's a hydrogen. So here, hydrogen's in the front, but it can't be in the middle because it's only capable of having 1 bond, 2 electrons attached to it. So we're going to put the next atom after hydrogen as our center. So in this example, that will be oxygen. And then we're going to attach hydrogens with 1 bond each because we just figured out we need 2 bonds. Okay, so we have 4 bonds that are involved in electrons. We had 8 originally. So I need to include 4 more electrons as unbonded. They like to pair up if they can, but we're going to still follow that same rule of trying to fill in one side at a time. So now I should have a total of 8 electrons if I followed the process right. We have 2 here, 4, 6, 8. So this has 8 electrons. There's a lot of different ways to draw Lewis dot structures that are correct. So if you do this, this will work too. If you do this, this will work too. Okay, so there's a lot of, as long as you have the right total number of electrons, the right number of bonds, we're good to go. All right, so NF3 is our next example. And again, we're going to look at the periodic table and see that nitrogen is in group 15, so that has 5. Fluorine is in group 17, so that'll have 7, but there's 3 atoms of fluorine. So we have 26 electrons to play with here. If everybody had their octet, that would be 4 atoms times 8, so we would have 32 electrons. So I can subtract them. We're going to find out that 6 electrons are in bonds, and so that means I'm going to have 3 bonds. Nitrogen is not hydrogen, so that'll be in the middle, and then I'm going to just attach each fluorine with a bond, because we said 3 bonds, and there's 3 atoms to attach. Then, to figure out how many extra electrons I have, I've got to be like, okay, well I had 26 to begin with. I used 6 of them in bonds, so I got to fill in 20 electrons in this structure. It's important to do this where the outside atoms, not the central atom, the outside atoms are going to have their octet filled first. So right now, fluorine has 2 electrons that it's sharing with nitrogen, so it needs to have 6 more. And that's going to be true for all of the fluorine. So to complete the octet, I got to add 6 more electrons to each fluorine. So we're going to do that. And you'll notice I'm being really neat. You should be too when you're writing these on paper, especially for lab. All right. right, so we've got 8 here. 2, 4, 6, 8. We have 8 here. So 10, 12, 14, 16 total. And then another 8 here. So 18, 20, 22, 24 electrons. So far, I have used a total of 24 electrons, including our bonding. We have 26, so now I will turn my attention to the center atom. They're the last one to worry about. In this case, we're able to get an octet for everybody. The nitrogen has, let me do this in blue. The nitrogen has an octet with 6 electrons shared in bonds and 2 that belong just to the nitrogen. And each fluorine also has an octet because it's sharing 2 electrons and it has 6 on its own. Okay, so that is how you draw these Lewis dot structures. Don't do this one, skip that one. We're going to do HCN together. So H has 1, carbon has 6. No, that was wrong. Oxygen has 6, carbon has 4, and nitrogen has 5. So all together, we're going to end up with 10 electrons. If everybody had what they wanted, so hydrogen wants 2, and carbon and nitrogen both want 8, so then we would have 18 electrons to play with. So we'll subtract those to figure out how many electrons are in bonds, and then we'll divide by 2 to figure out how many total bonds there are. So we have 4. Hydrogen cannot be the center atom, so we're going to make carbon the center. We'll start by just connecting hydrogen and nitrogen. That's only 2 bonds, though. I can't put any more bonds on a hydrogen. Hydrogen can only handle 2 electrons, which is 1 bond. So I have to add our other 2 bonds between the carbon and the nitrogen. So we have 3 lines. This means 6 electrons are shared between carbon and nitrogen. We call that a triple bond. That's the highest you can go. There is a such thing as a double bond, which would be 2 lines between carbon and nitrogen. Triple bond is, we can't have anything more than that because there's not enough space. The orbitals are occupying everything around the carbon and nitrogen. So triple is as high as we go. So you can have single bonds like this one, showing 2 electrons shared. You could have something like this, double bond. And in this case, between carbon and nitrogen, we have a triple bond, okay, because that's what we calculated. So that leads us to the last step. We had 10 electrons to begin with. We put 8 of them in bonds. So we have 2 electrons left to account for. Now, I said earlier that carbon will never have more than 4 bonds or less than 4 bonds. It's always 4. So here we have 1 between the hydrogen and carbon and 3 between the nitrogen. So that is a complete octet. It's 2 electrons, 4, 6, 8, just like that. So the carbon's happy. The nitrogen only has 6 electrons assigned to it right now. So we're going to take our other 2 electrons and put them onto the nitrogen. And that means now nitrogen has an octet, hydrogen is complete, so everybody's happy. So this is hydrogen cyanide. There are other methods to get to the same Lewis dot structure, as I have mentioned before, such as just trying single bonds and seeing if that works, and trying double bonds, see if that works, on and on. I think this one is the least frustrating, but that's for me. So if this doesn't work for you, come and see me and I will show you the other ways.